Okay, we're rolling now. Did you get that? We are recording now.
Okay. So for today's session, we'll be talking about Laplace transform and inverse Laplace transform. First thing to note is while taking Laplace transform, there are two ways. One is bilateral and the second is unilateral. So bilateral works for both causal and non-causal signals, which means that our integration runs from minus infinity to infinity, f of t e raised to the power minus st dt, and this is our Laplace transform f of s. Okay. Now in unilateral, we only have causal signals. That is, they are present only for t greater than equal to 0. Okay, so our Laplace transform now is from 0 minus to infinity f of t e raised to minus st dt. And whenever we'll talk about Laplace transform, we would be referring to unilateral. Okay, and in the textbook there's a table which gives the Laplace transforms for some standard functions. For example, for delta function, we'll have the Laplace transform is 1. For the step function, it is 1 over s. For the ramp function, it is 1 over s square, and so on. So these are the standard functions that we'll be using throughout the class for Laplace transform and taking the inverse Laplace transform. Okay, now I'll just show you how to take the Laplace transform of a function which is of the form e raised to minus at u of t. So it's a decaying exponential and causal since we have u of t term here. Okay, so we will be taking the unilateral Laplace transform. Okay, so our f of s is now 0 to infinity e raised to minus at e raised to minus st dt. Oops, sorry. Okay. Now moving forward, we'll have e raised to minus s plus at dt. Right? And this integrates to 1 over s plus a e raised to minus s plus at 0 to infinity. Okay? And there will be minus n. Right? Now I'll just write that thing again over here. Sorry, minus 1 over s plus a e raised to minus s plus at 0 to infinity. Now when we talk about Laplace transform, we have a term called ROC, that is region of convergence. Region of convergence only means whenever this integral f of s is finite. It's not going to infinity, it's converging to some finite value. Okay, so how do we find the region of convergence in this case? This is just a constant term, and do not forget that s is complex over here. Okay, so our e raised to minus s plus at term is the governing factor for defining region of convergence, right? Now here the region of convergence will happen whenever the real part of s plus a is greater than 0, right? When this happens, then my e raised to minus s plus a raised to t term goes to 0 as t goes to infinity, correct? Right? So this is my region of convergence. Now what does this mean? In the complex plane, anything to the right of my imaginary axis is my region of convergence. Okay, so this is my ROC, this is the real axis, this is the imaginary axis, and the origin. Okay, so that's what the ROC means, right? So now with that thing done, so if another factor to note is that if my signal is finite, right? So if my signal, for example, is like u of t minus u of t minus 4, okay, this is a finite signal, it's not infinite. Whereas e raised to minus at was not a finite signal, it was going up till t equal to infinity. Okay, so this was infinite and this is finite. So whenever my signal is finite, my region of convergence is the entire complex plane. Why? Because my function, which is the governing factor, that itself is finite. So when my function is finite, it will integrate to a finite value. So the S factor does not play any role at that point of time. That's why my whole region of convergence is the entire complex plane. Okay? All 4 quadrants? Yes, all 4 quadrants. Alright? Because if you see here, the imaginary part does not play a role because the magnitude of imaginary part is always 1. Oh. Right? That's why we are only looking at the real part. Okay? Now moving forward, we'll talk about taking the inverse Laplace transform. So for inverse Laplace transform, we do not perform integration again, rather we take the term functions that's given to us in the Laplace transform domain and then break it up into the standard form and then use the table to get back to the time domain. Okay? So by definition, my f of t is 1 over 2j c minus j c plus j infinity f of s e raised to power st ds. Okay, so earlier it was f of t over here and e raised to minus st dt, and now it's f of s e raised to power st ds, right? Because we're in S domain, we will integrate with respect to x. When we're in the time domain, we'll integrate with respect to t. Okay, but we don't use this integration to get our inverse Laplace transform. What we do rather is our partial fraction expansion. Okay, so I'll go over a few examples and then you'll get a better idea of what I'm talking about, right? Now, just to be clear about some terms, our f of s is given in the form of a fraction like p of s over q of s, some numerator in terms of s and another denominator in terms of s. When you solve the numerator, that is equate p of s to 0 and solve for s, you will get zeros. The term is called zeros. The solutions for this equation is called zeros. Whereas if you do the same thing with q of s and then solve for s, these are called poles. Okay? So zeros are the values of s for which f of s is will be 0 when you substitute those values, and poles are the values of s for which f of s will be infinity when you substitute those values. Okay? Right. Now moving forward, let's do an example. Okay, so if it's given to us that x of s is 7s minus 6 upon s square minus s minus 6. Okay, so first step is to factorize the denominator. Okay, so we will factorize the denominator. That's the first step. Okay, and these are standard steps, so you'll follow the same steps in all cases, right? So what do we get after factorizing? We'll get 7s minus 6 s plus 2 and s minus 3. Okay. So now we have poles at two locations. That's at poles are at s is equals to minus 2 and s is equals to 3. Correct? Because if you put minus 2 or 3 here, my x of s will go to infinity. Okay. Now we have this. Now the partial fraction expansion, we'll write this in the form of x of s is equals to k1 upon s plus 2 plus k2 s minus 3. Okay. Now with that done, the next step is to do the following. So first to find k1. Now next step is to find k1 and k2. Okay. So to find k1, we will multiply this term of x of s with s plus 2 and substitute s equals to minus 2. Okay. So for k1, multiply by s plus 2 and substitute s is equals to minus 2. Okay. Now doing that, we will get k1 is equals to 7s minus 6 over s plus 3 at s is equals to minus 2. Okay, solving this we'll get 4. Okay, and the same thing we'll do for now for k2. Okay, so same for k2. That's my third step. So now my k2 will be 7s minus 6 over s plus 2 at s is equals to 3. Okay, now this will be 3. Right? So now my x of s has been written in the form of 4 over s plus 2 plus 3 over s minus 3. Right? And from the standard Laplace transform pairs that we have and the one that we just solved, for e raised to minus at u of t, my Laplace transform is 1 over s plus a. Okay, so using this over here now. Okay, so now my x of t will be 4 e raised to power minus 2t plus 3 e raised to power 3t u of t. Okay, so here I'm just substituting, I'm using this formula and substituting it back. So I have minus s minus minus 2 s, right? So this 2 will go back here, so a is 2 now, and then this minus 3 will go back here. Okay, yeah, right. So this was the case where we had real and distinct roots. Okay, so we had real and distinct roots, or poles to be correct. Okay, so let's do another example now. This is pretty much similar, so another example. So x of s is now given to be 96 s plus 5 s plus 12 over s plus 8 s plus 6. So now my s denominator is already factorized, so I don't have to worry about that step right now. Okay, so what are my poles over here? So my poles are at s equals to 0, s is equals to minus 8 and s is equals to minus 6. Correct? Now again, doing the partial expansion thing, we will write x of s in terms of k1 over s plus k2 over s plus 8 plus k3 over s plus 6. There's one term for each of these terms. Okay, so do not ignore the s that you have separately outside. Okay, and again solving the way we had done before. So for k1 we'll multiply by s and then substitute s equals to 0. Okay, for k equal to 2 we'll multiply by s plus 8 and substitute s equals to 0. For k equal to 3, we'll multiply by x plus 6 and substitute s is equals to minus 6. Okay? So you'll get your k1, k2 and k3 from there. So x of s will then be 120 over s minus 72 over s plus 8 plus 48 over s plus 6. Okay? And then again we will use this standard formula back over here. So 1 over s, so Laplace transform of ut is 1 over s. Okay? Right? So all of these formulas that I'm using are from the standard transform pair table. Okay? So you will have access to this. Right. So now my final x of t is 120 minus 72 e raised to power minus 8t. This is again using the formula that I had used in the previous example, and then plus 48 e raised to minus 60 u of t. Okay. So thing to note is do not leave the s factor that's there outside, right? And again, there could be a mixture of transform pairs that you have to use. So here you had ut and here you have e raised to minus 80 transform pair. Okay. Now moving on, our poles can be complex also. So let's look at that for a case. Okay. So if x of s is equals to 6s plus 34 upon s into s square plus 10s plus 34. Okay, sorry. Okay. Now this we'll factorize into 6s plus 34 upon s, and our complex poles will be conjugates of each other, right? Because our final answer is real. That's why our complex poles are conjugates of each other, right? So this and this are conjugates of each other. Okay. Now this is the case of complex distinct roots. So roots and poles, I'm referring to the same thing. Okay. Now again I'll write x of s as k1 over s plus k2 over s plus 5 minus j3 plus k3 over s plus 5 plus j3. Okay. Now k3 will be the complex conjugate of k2. Okay, that's another thing to note. So k3 is equals to complex conjugate of k2. So you don't even have to bother finding k3. You just find k2 and then take the complex conjugate of it. Okay. So now to find k1, we'll multiply our term with s and substitute s is equals to 0. That's the standard step. So 6s plus 34 s plus 5 minus j3 s plus 5 plus j3 at s is equals to 0. Okay, and this gives me k1 is equals to 6. Right. Now for k2 and k3 we do the same thing. So for k2 I get minus 3 plus j4, and k3 is the complex conjugate, so I'll get minus 3 minus j4. Right. Now when you have complex roots, the first step is to convert k2 and k3 to polar form. Okay, so convert k2 and k3 to polar form. Right, so my polar form is 5 e raised to power j 126.9 degrees over here. I'm writing in degrees right now. Okay, so my x of t is equals to This was 6 over s. 1 over s is the Laplace transform of u of t, right? So I'll have 6 u of t plus, when you have this will give me a complex exponential, and this term will also give me a complex exponential, which will be complex conjugates of each other, right? When you add two complex conjugates, you'll get cosine term, right? So that's how you get 10 e raised to the power minus 5t cos 3t plus 126.9 degrees u of t. Okay? 6 ut is from this k1 over s, right? Okay, so this term is nothing, it's coming only from k2 and k3. K2 and k3 are complex conjugates of each other, right? And when you add two complex conjugates, you'll get a cosine term. All right. Now, this is when we have distinct roots. We can have repeated roots as well. So another case of repeated roots is if we are given x of s is equals to 8s plus 10 over s plus 1 and s plus 2 cube. Alright, so when we write this in partial fraction expanded form, we will write it as follows. First we'll have k1 over s plus 1, that's standard, right? Next we'll have k2 over s plus 2 cube, that is also fine. Next we will have k3 over s plus 2 square and k4 over s plus 2. Okay? No, this is just to make sense out of it. You can start with this also. These are just constant terms. Just be sure that you are accounting for these terms, right? So now how do we solve for k2, k3 and k4? k1 is our standard solution. So k1 you multiply with s1 with s plus 1 and substitute s is equals to minus 1. Okay, k2 is again standard, you multiply with s plus 2 cube and substitute s is equals to minus 2, right? For k3 and k4 there's a slight difference in our computation. We will first take the derivative of 8s plus 10 over, one second, let me verify this once. Yeah, over s plus 1. Okay, first you take this derivative, right? And I'll just show you how to take the derivative just to recap. And then substitute s is equals to minus 2. Okay, so first take derivative and then substitute s is equals to minus 2. Okay, all right. For the, let me go further.
Are you taking the derivative of
With respect to s, yes. So what do we have? We have 8s plus 10 over s plus 1. This is the term we have, right? How do we take the derivative? Basic chain rule. Okay, so first we keep 8s plus 10 the way it is, right? And take the derivative of 1 over s plus 1, that is minus 1 over s plus 1 squared, right? Next we keep 1 over s plus 1 the way it is and take the derivative of 8s plus 10, that is just 8. Okay, this is our derivative term. Okay, now we substitute s is equals to minus 2 in this. right? So substituting minus 2, we will get minus 6 into minus 1 over minus 1 squared plus minus 8. Okay, so this is 6 minus 8, so we'll get minus 2. Alright, so that's my K3. This is K3. So for K4, you will take double derivative. Double derivative is just taking the derivative twice. After taking the derivative twice, then you substitute s is equals to minus 2. Okay? Right? And then we'll substitute all of this back into the equation. Let me just pull up the final answer. Okay, so my K4 is also equals to minus 2, right? So my XS is finally 2 over S plus 1 plus 6 over S plus 2 cube minus 2 S plus 2 square minus 2 S plus 2. Okay, now my XT will be 2 e raised to power minus t plus 3t square minus 2t minus 2 e raised to power minus 2t this whole u of t. This 3t square, 2t are coming from the squares and the cubes that we have here. This is again in the standard form, so I'll just show you the table. Oh, wait a second. Huh. Yeah, I think that should be 6. Let me check it. So our standard form is t e raised to power lambda t u of t has a Laplace transform of 1 over s minus lambda squared. Okay, and if t is of some other power, we have et n factorial over s minus lambda. I believe it's n plus 1. Yeah, so the 6 should be there, I think so. One second. T square, so n is 2 over here, so 2 factorial is 2, that's why there's only a 3 term. So the 6, 3 is, the other 2 term is coming from this equation. So we'll have t square, so I'm just expanding this now, okay? Sure, yeah. So t square e raised to minus 2t u of t, okay? This will have a Laplace pair of 2 factorial over s plus 2 cube, right? Which is 2 over s plus 2 cube. This is then multiplied with 3, which will give us 6 over s plus 2 cube. Okay? Yeah, so 3 is just a constant now. Okay? 2 is coming from within the function when we take its Laplace. Yeah. All right. So for repeated roots, we take the derivative. So if our original factor is of a cube, we take its first derivative when we are computing s plus the second degree factor, and then take its double derivative. So you take your you take more number of derivatives as the degree decreases. Okay. So original degree is 3. You go to 2, you take first derivative. Then you go to 1, you take derivative 2 times. All right. So that's how we proceed. Now let's go over. Now I'll just go over a few small things. So Laplace is itself Laplace transform is linear. Okay, so if I have two functions, let's say x1t and x2t, okay, and I generate so basic linearity check, right? So I'll generate a new function called xt, which is ax1t plus bx2t, and I'll take the Laplace transform of this xt. Okay, so my x of s is equals to 0 to infinity or minus infinity to infinity. Let's take bilateral. ax1 xt e raised to minus st dt. Okay, that's my Laplace transform formula, right? And also x1t has its Laplace transform, which is x1s, and x2t has a Laplace transform, which is x2s. All right. Now we'll write this as integral minus infinity to infinity ax1t plus bx2t e raised to minus st dt. Right. Now we'll break up the integral into summations. Okay, so two separate integrals now. So ax1t e raised to minus st dt plus bx2t e raised to minus st dt. Okay, so a will come out as it's a constant. We will have x1t e raised to minus st dt plus b x2t e raised to minus st dt. Right? Now this itself is Laplace of x1t, and the second term itself is Laplace of x2t. So this is x1s and x2s. All right. So our final answer is ax1s plus bx2s. Right. So our Laplace of our function xt summations of Laplace of the individual functions. So it's linear. It satisfies the additivity and homogeneity property. Alright, so Laplace is linear for us. Now I'll just go over quick MATLAB demos to perform inverse Laplace transformation using MATLAB, and after that I'll go over some properties. So for the first MATLAB example, let me write down the function. So x of s for my first example is 2s squared plus 5 over s squared plus 3s plus 2. Okay. So we know how to do this manually. We'll just see how to implement this using MATLAB. All right. So let me just switch to laptop. Okay. So 1 second. I have my standard script running. So this is my x of s, which I had just written, that is 2s squared plus 5 over s squared plus 3s plus 2. Right? So the first step is to define the coefficients of the numerator and denominator terms. Right? So in my numerator, the highest degree is 2, there is an s square term, right? So the s square term has a coefficient of 2. There is no s term, so that's why we have a 0. And then there's a constant term, so we have put up a 5, which is 5. Okay? Now we do the same with the denominator now. So s square has a coefficient of 1. S has a coefficient of 3, and then we have a constant term of 2. Okay? So this way we've defined our numerator and denominator, right? So MATLAB has an inbuilt function called residue, which performs the partial fraction expansion for us. Okay? I'll just give a brief description in a bit about how residue works. So what do we supply residue with? The inputs are our numerator and denominator. Be careful with the order. Do not put your denominator before the numerator. Okay, so first supply your numerator and then your denominator. Okay. This function returns us 3 things, R, P and K, as it says. So R is the residue values, which we were using as K1, K2 in our partial fraction expansion method. Okay. P is the pole values, which is where our poles will occur, and K is the constant terms that are left, okay, which have no factor of s in them, right? So let's look at this and see what results do we get. I'm just going to run it. Okay, so we get R is equals to minus 13 and 7, P is equals to minus 2 and minus 1, and K is equals to 2. So let's see if we actually get this answer when we do it ourselves. Okay, so first step is to factorize the denominator, right? So 2s square plus 5 over s plus 1, s plus 2. So we know we are correct that we got poles at minus 2 and minus 1, right? So poles at minus 2 and minus 1. So one part of our answer is correct. Next is to write this in partial fraction expanded form. So k1 over s plus 1 plus k2 over s plus 2, right? So k1 will be 2s square plus 5 over s plus 2, and putting s is equals to minus 1, right? So it will be 2 minus 1 square plus 5 over 2 minus 1. So 5 plus 2 is 7, correct? So one answer is correct for us. Next is 2s square plus 5 over s plus 1, and we put s is equals to minus 2, right? So we'll have 2 into minus 2 square plus 5 over minus 2 plus 1. Okay, so we'll get minus 13. So second part of our answer is also correct. Okay, and then sorry, okay, right? So our final answer, one second, x of s is 7 over s plus 1 minus 13 over s plus 2. All right. I'm so sorry. So x of t will be 7 e raised to power minus t minus 13 e raised to power minus 2t u of t. Okay. All right. So it matches the answers that we had got. Now we can go forward and look at another example. One second, let me just switch over. So here is another example. Now my XS is defined. So xs is defined to be now 2s square plus 7s plus 4 over s plus 1 s plus 2 square. Okay, so now my numerator has coefficients of 2, 7 and 4. Okay, and my denominator is factorized. Okay, so my first step is to write the coefficients of s plus 2, which is 1 and 2, and since it's squared, so we convolve these two. We use the conv function to convolve them. Okay, here it's working as multiplication, right? So this term corresponds to my s plus 2 square term, okay, which is then multiplied with s plus 1. So there's another convolve function, right? Okay, that's how my denominator is defined now. And then we supply it again to the residue function and we'll get the answer. So now my residues are 3, 2 and minus 1, that is k1, k2 and k3 are 3, 2, minus 1. My poles are at minus 2 and minus 1, and then there's no constant term. Okay? All right. Another thing to know is that, one second. I made a mistake. Since our x of s over here, the one we had done previously, the 2s square plus 5 over s square plus 3s plus 2, the degree of numerator and denominator is same, that is 2, right? So we can't go forward with the partial fraction expansion when the degree is the same, right? So for this, the degree of numerator has to be less than the degree of denominator for partial fraction expansion. Whenever the degree is the same, you will have a constant term. Okay? So the constant term will have a Laplace transform, inverse Laplace transform of delta t. So you'll have a constant term.
And that's the degree.
Yeah. So whenever the numerator degree is equals to the denominator degree, you will have a constant term.
To say the degree was like your third power, so would the constant term be 3
No. So here what we've done is you write this as 2s square plus, no, one second. So s square plus 3s plus 2 plus x. So you write this in this form, something, let's say y plus z over s square plus 3s plus 2, mixed fraction sort of a form. Okay, so s square plus 3s plus 2 into y plus z will be this. Okay, so what will this be? This will be, so y has to be 2 because you have a 2s square term in over here, right? So y has to be 2. So what you'll have in the numerator is 2s square plus 6s plus 4 plus z, right? And this thing has to be equal to 2s square plus 5. Because this thing is getting multiplied with the y, right? And y has to be 2 because here the coefficient is 2.
Oh, so the 2 you just whatever the coefficient.
Yeah, highest degree is. Okay, so here my z will be now, this thing gets cancelled, will be minus 6s plus 1. right? Okay, so let me do this again before it gets confused. Okay, so let's start with xs is 2s square plus 5 over s square plus 3s plus 2, right? So it's same degree, so we need to reduce the degree of our numerator. That's the first step, right? So we'll write it as 2 plus some z over s square plus 3s plus 2. Okay, now z has to be 2s square plus 6s plus 4 is equals to 2s square plus 5. Okay, sorry, there's a z term also. So z is equals to minus 6s plus 1. Alright, so now my xs is minus 6s plus 1 over s square plus 3s plus 2. So leave the 2 for now. Okay, 2 is there, we leave it. We'll go forward with the partial fraction expansion of this term. So k1 over s plus 1 plus k2 over s plus 2. Okay, now k1 will be minus 6s plus 1 over s plus 2 at s equals to minus 1. Okay, now this becomes 7, correct? K2 will be minus 6x plus 1 over s plus 1, s is equals to minus 2. This will be minus 13, correct? Now my xs is finally 2 plus 7 over s plus 1 minus 13 over s plus 2. Okay, now xt, my Laplace transform of delta t is 1. Okay, so if I have a constant in my xs function, it will inverse transform will be 2 delta t, and it will be 7 e raised to the power minus t minus 13 e raised to the minus 2t u of t. Okay, all good now? All good? Okay, so coming back here, that's what we have written here. 2 delta t plus 7 e raised to minus t and minus 13 e raised to minus 2t u of t. Okay, so whenever the degree is same, you will have a constant delta term. Okay, now for the second one, my k, there was nothing in k, so I don't have any constant term, right? So I don't have any delta function in my answer. Okay, right? Now I'll go over some properties of the Laplace transform. Okay, so let's come back. First is the time shift property. Okay, so let me pull that up. So what does the time shift property say? It says that if we have some function xt which has a Laplace transform of xs, capital Xs, then if we shift our xt by some time constant t0, okay, so t0 is our time shift that we are applying. Okay, so if our shifted function looks like t minus t0, x of t minus t0, its Laplace transform will be x of s e raised to the power minus s t0. Okay, so if you apply a time shift over here, it manifests itself as an exponential term. If you change the sign to plus t naught, it will be e raised to power s t naught. Alright? Now, you have a homework question which is to prove why this is the case. So, that's what you'll do. I won't be discussing the proof here. The next property is frequency shift. So what will happen if you shift in the frequency domain and you look at the time domain? Okay, so next is frequency shift. Right, so again, x of t has a Laplace transform of capital X of s. Okay, and now I apply a frequency shift over x of s. Okay, so s naught is my frequency shift. This will have an inverse Laplace transform of xt e raised to power s naught t. Okay, so time shift also results in an exponential in the frequency shift, and frequency shift also results in an exponential in time domain. The signs are opposite. Be careful with that. Alright, so here t naught is greater than equal to 0 and here s naught is greater than equal to 0, positive in these cases. Okay, now there's time derivative property. What if we take the Laplace transform of the derivative of the function, also called time differentiation property? Okay, so if xt has Laplace transform x of s, then the derivative of x has Laplace transform s x of s. Okay, it gets multiplied with this, and as this derivative term increases, that means you take more and more derivatives, this degree keeps on increasing. Okay, and then you subtract an initial condition. So this is value of x at 0 minus. 0 minus is nothing, it's just a very minuscule time before 0. 0 plus is a very small time after 0. Okay, that's what it means. Right? So if this is some nth derivative of x of t, that will have a Laplace transform of s raised to power n x of s minus s raised to power s minus 1 x0 and so on. Okay, this is derivative, this is the n minus 1th derivative of x. Alright, yes, so the dot represents the first derivative. Okay, and similarly you have an integration property. What if you take the Laplace of the integrated function? So if xt has Laplace transform x of s, then its integral 0 to x of tau d tau has a Laplace transform of x of s over s. Okay, so when you're taking a differentiation, x of s gets multiplied with s. When you take integration, it gets divided by s. Alright, now convolution property. If you have two functions like x1t convolving with x2t, and you want to see what's the Laplace transform of this convolution, and x1t has Laplace transform x1s and x2t has Laplace transform x2s. Okay, these are already given to us. These we already know that they individually have these Laplace transforms. The convolution Laplace transform will then be x1s multiplied with x2s. Okay, so convolution in time domain becomes multiplication in frequency domain, and convolution frequency domain will become multiplication in time domain. So if you have x1t multiplied with x2t, its Laplace transform will be convolution of x1s with x2s. Alright? So these are golden rules. Convolution in time domain becomes multiplication in frequency domain, and convolution frequency domain becomes multiplication in time domain. Okay. And these properties are again listed in the textbook if you want to look at it further. And that's for it today. I'll be here for my office hours. Thank you.